to a new session of basic electrical engineering. So the syllabus is common for AIML and the sister like courses like cyber security or data science or computer science and design or a business system. So in BTech, these are the new streams which were introduced by JNTU, and for that the common syllabus under Unit 2 is AC circuits. In our class 1, we have seen the basics of R, L and C. In this class, we are going to see the combination of RL, RC and RLC. So from our basics, if at all we recall, we have seen the difference between the voltage and current relationships, whether it is passive element resistor, inductor or capacitor. For that, the input supply voltage in AC form is same. You can see here the input voltage or the instantaneous voltage is equal to Vm sin omega t for all the passive elements, that is resistor, inductor and capacitor. Where if at all you take the instantaneous value of current, the current is Im sin omega t for resistor. For inductor it is Im sin omega t minus pi by 2 means 90 degrees. And for capacitor it is Im sin omega t plus pi by 2. And if at all you look into the waveforms of the phasors, you can see the voltage and current for resistive load or a pure resistive load when input supply is AC. You can see the relation of phase voltage and current is in phase. That is the starting point of voltage waveform and the current waveform, the maximum value, the minimum value, and for complete one time period it is one and the same, only there is a difference of the amplitude. When you talk about a pure inductor, you can see the voltage and current relations, where you can see the current lags voltage. The red sine wave is the voltage, the blue sine wave is the current. Now current lags voltage by 90 degrees. Pi by 2 it's an electrical radian degree. And if at all you take up your capacitor, you can see the current leads voltage. So this is what we have learned in our previous class. Now with this basic concept, we'll jump into the RL circuit. You can see here instantaneous voltage value is applied to an RL circuit, which is a series RL circuit. And current, when it starts flowing, it develops a voltage across resistor and across inductor as VR and VL. So if at all you apply a KVL for the input supply voltage, that will be equivalent to VR plus VL, that is the developed voltage across resistor and inductor. So the supply voltage is equal to VR plus VL, and if at all you substitute the formula in the rectangular form, it is R multiplied with I for drop across resistor and J XLI, that is a drop across inductor. Now in this common thing is that I is the common current which is flowing through this RL series circuit. So I'll take I common and I'll divide by the voltage, then I'll get the value of impedance, where Z is equal to R plus JXL. Now this is the value of impedance in rectangular form. So the voltage across resistor is in phase with the current, whereas voltage across inductor leads current by 90 degrees, what we have learned from our last class. Now the total impedance, if at all I look into the polar notation, it is the magnitude of impedance and the angle between voltage and current, that is given by phi. So the magnitude value of the impedance is given by under root of the real component square plus the reactive component square. So here XL is the inductive reactance whose value is omega L. Square indicates the term square term. Omega indicates the angular frequency, and the angle between, that is the power angle between reactive component and real component, is given by tan inverse XL by R. Now if that is true, how to understand the behavior of the resistive and inductive in nature of a passive element, where a resistive you have voltage is in phase with current, and when you talk about inductor, the inductor lags voltage by 90 degrees, or I can say the relationship between voltage and current is out of phase. So we have to combine these two for RL circuit. So for RL circuit, the resistance has a current which is passing through it, and that is in phase with the voltage. Therefore, the developed voltage across resistance is VR, and the current which is in phase with VR is I. So this is in phase with R, whereas in inductive circuit you have the resistance which is in phase with current, that is the resistance voltage which is in phase with the current, whereas the voltage across inductor leads current by 90 degrees. So I have to take the component of VL perpendicular to this straight component, that is X component, and combination of VR and VL will result in V. Hence, the angle between the voltage and current is related by phi, and this is a notation for out of phase. Now, if I take a voltage triangle, this is how it looks like, and the impedance triangle, it looks like this, and the value of power factor, which is nothing but the cos of phase angle, which is nothing but the real component of the system divided by the total impedance of the system. So the power factor is given by R by Z. Now let us calculate the instantaneous power, which is given by instantaneous voltage and instantaneous current. I'll substitute the value of voltage and current for RL circuit, and I'm left over with the power value, which is equal to Vm Im multiplied with this, the cos phi minus cos 2 omega t minus phi by 2. This elaboration is done with the help of sine AB formula for power calculation. What is the conclusion we can make from this power equation is that the frequency of the fluctuating part is twice the applied voltage frequency, and its average value for one cycle is 0. That is understood. So the value of P average or average power or true power is nothing but Vm Im by 2 cos phi. And if at all I take the components of RMS conditions, then Vm by root 2, Im by root 2, I can take this mathematical equation and I can represent the RMS value of power as Vi cos phi. So for RL circuit, you can see the current waveform lags the voltage. Now the average power is treated as the active power, and this power is dependent upon in phase of the current condition, and the reactive power is denoted by Q. And if I want to take the values of active power and reactive power, I'll take the help of power triangle, which is given by this diagram. You can see the power, it is given by as I square R, the reactive power is given as I square XL, and the apparent power is given by S. How we have framed these equations? In the triangle, we know that the cos phi is R by Z, and we know that the V is equal to Z into I. I'll take the value of power calculation as Vi cos phi, and I'll substitute the above two formulas, and I'll get a real power which is I square R, and the reactive power I'll get as I square XL, and the apparent power I'll get as I square Z. Hence, from this triangle, we can get the value of power factor either in terms of resistance, either in terms of voltage, or either in terms of power. So this is how you estimate the power factor for a single phase AC applied to RL circuit. Now come back to RC circuit. Now you can see here we have a RC network which is connected in series, and when the current starts flowing, the developed resistance and voltage and developed capacitance voltage, it is given by VR and VC respectively. And if at all you take the impedance condition, impedance will be equivalent to R minus JXC, and clearly here the voltage across capacitor lags current by 90 degrees. And if at all I want to know the impedance conditions, the magnitude of impedance is given by under root of R square plus 1 by omega square C square, and the angle between the current and voltage is given by tan inverse XC by R or 1 by omega RC. Now look into the phasor diagrams. Unlike RL circuit, you can see that RC circuit has a impedance triangle, voltage triangle, which is in this form, and the value of real power, reactive power, and apparent power are given by the same relations, and the power triangle and the voltage and current relations, you can see that the current leads voltage by 90 degrees for RC circuit. If at all you can look into the numericals to understand the better way, I have first analysis of RL waveform and circuit in this form, and RC and the waveform of RC in this form, and I'll apply to a problem where I have a alternating voltage of 20 plus 30 J volts applied to a circuit, and a current it is flowing in the circuit, it is nothing but 2 minus J amperes. We have to find the impedance, phase angle, power factor and power consumed by the circuit. For that, I take the data which is given to me. So the rectangular form value is given as 20 plus 30 J volts. The current value is given as 2 minus J amperes. So the polar form of rectangular value is 36.05 at an angle 53.09 for voltage, and for the current it is 2.2 at an angle minus 26.56. So I'll calculate the impedance value, which is easier, and that is obtained in rectangular form as 2 plus 16 J ohms. You can easily convert into a polar value, which is 16.12 at an angle 82.87. With that, I'll get the impedance value in magnitude form as 16.12 ohms, and the phase angle value is 82.87. So the impedance value and phase value is calculated from A and B. The power factor is given by cos phi. So simply you apply the value of 82.87 under cos. You're going to get the value as 0.124. Remember, it's a RL circuit, so the power factor is lagging. And the power value is given by VI cos phi. Substitute the value and going to get the value of power as 9.99 watts. In the second problem, you can see we need to find out the value of power factor and the average power delivered to the circuit. So I have taken the data and I have estimated the phase angle between the voltage and current, which is nothing but difference of the current angle with the voltage angle, that is the minus 60 degrees, and power factor will given me the value as 0.5, and I'll calculate the value of average power, which will be equivalent to 578.3 watts. In another problem, we have to calculate the reactance, power factor and power. So it's a RC circuit. We have the inputs as voltage and current. We have changed it into the polar form. Then we have estimated the impedance in polar form. Then we have taken the magnitude of impedance and we have converted the polar form into the rectangular form. With the help of rectangular form, we are able to calculate the resistance and the capacitive reactance. And finally, power factor is also helpful to calculate that the power factor indicates that the capacitor and resistor series connected to AC will make the current to lead voltage. So the power factor is leading here and the value of power is 56.34 watts. Now we know what we have studied about RL and RC. If at all we take the combination of RLC, then what happens? So here you can see in an example we have taken here single phase applied to series RLC circuit. So for the series RLC circuit, the input voltage is the same, that is Vm sin omega t, and we know that for resistor VR and I are in phase, whereas the case of pure inductor, the voltage leads current, and for the capacitor voltage lags current. So total supply voltage is equal to the algebraic sum of these voltages, that is the voltage across resistor, inductor and capacitor, given by VR plus VL plus VC. So the phasor diagram, from our past analysis, we can take the current as reference and the resistor voltage is in phase with current, and we have to take the perpendicular, that is nothing but the leading or lagging conditions. So in inductor, the voltage lags current, voltage leads current and capacitor lags current, and the difference of VL minus VC is taken as the difference of the voltage, and with this we get the condition for leading and lagging. So you can see here, if inductive voltage is greater than capacitive voltage, then we take the difference as VL minus VC. And if the capacitor voltage is greater than the inductive voltage, then we take the difference as VC minus VL. So for the conditions of impedance triangle, this is how the triangle looks like. For inductor greater than capacitor, that is the inductor reactance greater than the capacitive reactance, and this is for capacitive reactance greater than the inductive reactance. So you have here the conditions for voltage and current, and for XL greater than XC we have I is equal to Im sin omega t minus phi. For IC greater than IL, for XC greater than XL we have I is equal to Im sin omega t plus phi. So the power triangle you can estimate like this. For XL greater than XC, and for XC greater than XL you can have a power triangle like this. And these are the waveforms for inductive reactance greater than the capacitive reactance, and the second waveform is capacitive reactance greater than inductive reactance. So the power factor either you can get from the voltage triangle, or you can get from the impedance triangle, or you can get from the power triangle. So in a general way I have represented all the triangles in the name of voltage, impedance and power in this diagram. So look into numerical, where if you have the values of resistor, inductor and capacitor supplied to 240 volts 50 hertz input, estimate the power drawn by the circuit. Okay, the values we are going to take as it is. We'll calculate the inductive reactance, capacitive reactance. Here you can see 6.28 ohms, 159.15 ohms are the values of inductive reactance and capacitive reactance respectively. Let us calculate the impedance value. If XL is greater than XC, we are assuming that the value is higher or lower based upon the calculations what we made here. Now for that, the rectangular value and the polar value of impedance is given by the value as 153.19 at an angle minus 1.1505 ohms. This is the polar form of the impedance. Now with this we'll calculate the phase difference as this value, that is 1.505. So for series current circuit we have the current formed as V by Z, which is nothing but 1.56. The circuit power factor it is obtained to be 0.99. The power drawn by the circuit is obtained to be 25.08 watts. And similarly we can calculate the reactive power, which is nothing but 373.58 VAR, the unit of reactive power. So this is how we calculate the power calculations for series RL, RC or RLC circuit. So I hope you like this session. Please share among this information among your friends, and subscribe to this channel and press the bell icon for the future notifications.